Earth is an extraordinary world and a story of success, a flourishing oasis in the boundless cosmic darkness. However, the lifeless worlds that surround us indicate that our earthly prosperity cannot last forever. While our star may seem peaceful at first glance, a new era is already dawning for the solar system. It's an era of change, a new chapter in history where the world we know today will exist no more. New times are already arriving for our entire solar system. In the solar system today, it has been approximately 4.5 billion years, the same age as its parent star, the Sun. Until this moment, many factors have shaped its structure and arrangement, especially the migration of its large planets and interactions with neighboring stars in the early stages of its life. However, looking far into the future, it is the changes in the core of the Sun that will ultimately determine the fate of the entire solar system. The Sun is a colossal, unimaginably powerful nuclear furnace that, at this very moment, is smashing hydrogen atoms, transforming them into helium atoms in the so-called main sequence burning phase. The main sequence is the primary stage of a star's life, generating a constant flow of light and heat that sustains and maintains the delicate balance of life on Earth, supporting its biosphere for just over 4 billion years. Though we may not notice this on the scale of human life, as the proportion of hydrogen in the Sun's core decreases and the proportion of helium increases, the Sun becomes hotter and brighter. Every billion years or so, our star becomes about 10% brighter and consequently 10% hotter. While in the long term, this will have catastrophic consequences for the entire solar system. In the near future, the equilibrium on Earth will be disrupted and the climate will change forever. Over the next approximately 600 million years, escalating coronal mass ejections from the Sun will disrupt the magnetic field, shake Earth's biosphere, and disturb its natural balance. Trees and other photosynthetic plants, which use carbon dioxide to produce oxygen, will wither and burn. As the Sun becomes hotter, its habitable zone, known as the Goldilocks zone where conditions for life like Earth's exist, will shift beyond the Earth's orbit. When this happens, the oceans will evaporate, turning into a hot atmospheric layer. Water vapor molecules rising upwards will be split into their constituent hydrogen and oxygen atoms due to intensified solar radiation before disappearing into space. In about 1 billion years, our once blue and teeming with life planet will be scorched and sterile. Almost all of its multicellular life will be annihilated. Approximately 1.4 billion years from now, the Sun's habitable zone will expand to encompass the orbit of Mars. Consequently, Mars will once again experience a temperate climate. As Mars warms up, it will release the frozen CO2 in its polar ice caps, densifying its atmosphere. However, due to the absence of core geological activity and a weak magnetic field protecting the planet from solar wind, Mars won't be able to retain this thick CO2 layer long enough to make the planet habitable. In the grand scheme of things, there is no survival prospect for the inner solar system. Due to the Sun's increasing activity, it will produce more powerful mass ejections. Mercury's orbital eccentricity will increase the most, causing it to deviate from its current orbit and transition to a highly elongated orbit that intersects the orbits of other terrestrial planets. Hence, Mercury might eventually collide with Venus or Earth. All of this will occur in approximately 1.5 billion years or so. Earth will be burned, and its biosphere will be annihilated, all due to a mere 15% increase in the Sun's brightness and radiation. That's not much, considering what will happen next. In about 3 billion years, Earth's temperature will resemble Venus's today. The atmosphere will become toxic, unfit for any form of life. Around the same time, something truly spectacular will happen. The Milky Way and Andromeda galaxies will collide. Right now, we are millions of light years away from the Andromeda galaxy, the largest galaxy in the local group, which is twice the size and has more stars than our own Milky Way. However, with each passing second, Andromeda is approaching us at about 110 kilometers per second, and in approximately 4 billion years, our galaxies will collide. As mentioned earlier, the proportion of hydrogen in the core of the Sun continually decreases as hydrogen transforms into helium. Consequently, in about 5 billion years, the hydrogen reserve in the core will begin to deplete. This will lead to the compression of the core and the outer layers of the star, heating the core even further, extracting the remnants of hydrogen from the outer layers. Eventually, the Sun's core will heat up to temperatures capable of reigniting its nuclear furnace. However, this time, much of the energy generated through nuclear fusion will be absorbed by the Sun. As a result of these processes, in approximately 5.5 billion years, the Sun will start expanding, increasing its size by tens and then hundreds of times compared to its current diameter. When the Sun exits the main sequence burning phase, it will become brighter. All this energy will be distributed across a vast, continually expanding surface. As a result, the outer edges of the Sun will cool to about 26 Kelvin, and the Sun will acquire an orange-red hue, becoming a red giant. By this time, the Sun will engulf Mercury and Venus. If they fail to avoid collision, both planets will be vaporized by the expanding Sun. After Mercury and Venus, Earth will be next on the list of destruction. Earth, too, will be engulfed by the expanding Sun. As the Sun expands, the snow line of the solar system will shift. This is another circumstellar region with a specific temperature where it is cold enough for volatile substances such as water and methane to exist in solid form. This ice allows for the formation of icy moons and ring systems around planets. Currently, the snow line is located between the orbits of Mars and Jupiter, but as the Sun transforms into a red giant, it will shift farther out, and the outer part of the solar system will heat up. There will be no more habitable Earth-like planets left, only gas and ice giants. At first glance, it might seem like life in the solar system has vanished forever, but in reality, this could mark the beginning of a new awakening of life on Jupiter and Saturn's moons. Each of these two gas giants in the solar system has at least a dozen satellites of various sizes orbiting them. They revolve around the two large gas giants, Jupiter and Saturn. These planets have moons larger than Mercury, composed of rock, ice, gas, and water. But currently, these are frozen worlds. However, as the Sun expands, these volatile-rich moons will begin to thaw and expand. For Jupiter, these are Europa and Enceladus, and for Saturn, it's Titan. Unfortunately, while Europa and Enceladus have extensive oceans, they lack an atmosphere, causing the melted water to simply escape into space. Nevertheless, in the solar system, there is a unique satellite with specific characteristics that make it the most suitable for the emergence of life. That satellite is Saturn's moon, Titan. Titan is Saturn's largest moon and the second largest moon in the solar system. Titan possesses a dense atmosphere consisting of nitrogen and methane, extending hundreds of kilometers above its surface. It has the densest atmosphere of any of the solar system's moons, making Titan a unique world. Its atmosphere consists of a lower layer of gaseous nitrogen and an upper layer of methane, which is broken down by solar ultraviolet radiation, forming a dense, nearly opaque haze that obscures the moon's surface from sunlight. What makes Titan special is that its surface remains cold. In addition to its protective atmosphere, its frozen surface is rich in organic compounds that could serve as building blocks for the emergence of new life. This is supported by data from the Cassini-Huygens mission obtained in 2004. Currently, the surface temperature of Titan is minus 177 degrees Celsius. It's so cold that methane rains from the skies, and the rivers, lakes, and seas are composed of liquid methane. The Sun is not large enough to undergo a supernova explosion when it reaches the final stage of the red giant. To trigger a supernova, a star needs to accumulate many heavy elements with a constantly increasing temperature. This process will continue until iron is produced. After that, the star will collapse in on itself and then explode. However, the Sun is not massive enough to synthesize anything heavier than helium from fusion. Therefore, instead of becoming a supernova, it will undergo size and brightness oscillations. During the red giant phase, the hydrogen-burning shell around the Sun's core will increase the core's total mass until it comprises approximately half of the remaining mass of the Sun. Inside this core, the pressure will eventually become great enough to initiate helium fusion into carbon. In about 7 billion years, this will lead to a phenomenon known as a helium flash, a very rapid, uncontrolled nuclear process in which helium quickly transforms into carbon. After this occurs, the Sun will be unable to further fuse carbon into heavier elements. Thus, nuclear fusion will subside, and the red giant will begin to contract. The Sun will contract significantly compared to its current size. This will raise the surface temperature of the Sun to approximately 47 Kelvin. Following this, there will be a stable phase of helium burning in the core, lasting for about 100 million years. But once the core's helium is more or less exhausted, the Sun will expand again, extracting fuel reserves of hydrogen and helium from its outer layers, leading to a second, larger expansion. This time, the Sun will expand to nearly 4 times its previous diameter compared to when it was a red giant. Once the sun expands to such sizes, it will cool down once again. This phase will last for about 30 million years, after which the sun will begin to lose mass. The outer shell of the sun will become unstable and then be shed and ejected into interstellar space. These layers will not explode but will likely turn into an emission nebula. This nebula will contain helium and hydrogen fused in the sun's core, enriching the stellar environment with gases from which future stars may form. While this mass loss event will be much more peaceful than a supernova explosion, the sun will likely push any remaining planets farther away from itself. Additionally, the sun's weakening gravity as it loses mass will cause any remaining planets to spiral into the darkness of interstellar space, freezing to their cores and becoming orphan planets. What remains of the sun at the center of the nebula will be a tiny sphere the size of Earth, composed of extremely compressed degenerate carbon and oxygen known as a white dwarf. This tiny star will never reach the temperatures required to melt any of the remaining elements inside, and as a result, it will remain stable for a very long time. Approximately 2 billion years later, the white dwarf will gradually cool down, transforming into a dark sphere. This will mark the final day of the solar system. No one will ever witness a sunrise or sunset from then on. Well, while the sun is still shining upon us, try to do as many good deeds as possible. Leave a comment on this video, give it a like, and if you enjoyed it, share it with your friends. Until new and even more exciting cosmic encounters.